Okay, so the result will be the following. So let C be a rigid mathematical picture. As we discussed, the large so presentable stable rigid picture. Then the case of localized motifs over C is also rigid. So this is a target of the universal localized invariants of cases over C. Let's still denote them by basically C perfect, but maybe it's better to denote them, let's say, completely generated, relatively completely generated. Yeah, so there is a universal localized invariant. Commuting with specific elements. Finite, so commuting with specific elements. Yeah, and then I will explain some maybe applications or applications of the proof also of the statement. Yeah, so in particular, see the corollary that the figure is realizable, which is quite unobvious from the definition. And maybe I'll explain why this in general is not completely generated. So, in general, not completely generated. And let me write an expectation which I just wasn't able to confirm, but just most probably that if C is not zero, which is a reasonable assumption, then this history is not completely generated. For spectra, actually, no, but just because I think for spectra you can do it. I mean, it reduces to some computation of refined invariants. I will comment on this. But let's say I certainly know that this holds for modulus over Q of x. For C, which is the right case of polynomials. And then, of course, it follows that this holds for over Z of x. Yeah, I mean, just with maybe with some more work, you can prove it, I think, over any non-zero ring. And I think even for any non-zero ring. Okay, but now let me explain the general idea. So first, yeah, the general case is actually kind of difficult. So let me consider the case when C is modulus over something. So C, which is modulus over some infinity. Then there are different ways to prove this, and I will explain the way to prove it over a ring, which generalizes to this general rigid case. And so recall we have these notions. Recall for well, the notions for a realizable K-linear history. Integral G. So the first, so this is due to Kanselich definitions. I mean, he formulated it for completely generated histories and even for modulus over algebras, but you can formulate it for a realizable history. So D is proper. Properness is of course a relative notion over K if evaluation is strongly continuous. We already had this notion, I just recall it. Evaluation functor is to K modulus is strongly continuous. And D is smooth if co-evaluation is strongly continuous, which means that basically the diagonal logic is complete. So it means co-evaluation of K is complete. Okay, so Yeah, and for a small category, so small category A, small k-linear category is smooth or proper, basically by definition, if so is its completion, so is incompletion. Okay, so now, recall that we briefly mentioned this. The category of k-linear categories, k-linear stable infinity categories, I just want to update. It is completely generated. And there are well-known statements that if A is finally presented, which means compact, then A is smooth. So this is due to Toyen and Vaquet. And also, if A is smooth and proper, then A is finally presented. And let me just briefly explain the argument for the first statement. The second is kind of very easy to check. Let me briefly explain the argument for the first statement. So we can assume that so A is perfect modulus over some algebra A. And suppose that this algebra A is finally presented in E1 algebras. Then, basically, to show that it is smooth, you just consider in system of trivial square zero extensions for any in system of bimodulus system Mi. So Mi is a bimodulus over A. We have so if you just take sections, so in E1 algebras, like over, you take mapping space in the case of E1 algebras over A, from A to the to A plus k-limit of Mi. So this one must be the same as k-limit of the mapping spaces in algebras over A, from A to A plus Mi. And this is the same as k-limit of derivations, these are just mapping spaces in bimodals from the bimodule of differentials to Mi. And this is also the same as mapping space in bimodules from the bimodule of differentials to k-limit of Mi. So this implies that this bimodule of differentials is perfect, but basically in this funny non-commutative version of differentials, we have that it's simply the fiber, the map from A tensor A to A. And so it is perfect, so A is perfect. So this is so I call this simple argument because we will need its version of a rigid base, which is not so standard, of a general rigid base. So we have this complete compact generation for the world of small categories, and all these compact objects are smooth. And now, surprisingly, it turns out that we can formulate a reasonable notion of nuclearity for categories. The definition k-linear category, k-linear stable category A, which lives in curve. B is nuclear if for any, basically if it's nuclear in the sense of in this definition of Dyson and Peter, which they made in the context of models of analytic rings, but it makes sense basically in any sufficiently nice completely generated symmetric model category. So basically we say that if we say that for any finite represented A, all the maps from A to B are trace plus. So more precisely, if we take the functors from A to perfect K modulus and multiply that by B over K, then this is equivalent to functors, K-linear functors from A to B. Now, surprisingly, it turns out that this is a very reasonable notion. So I will explain why this nuclearity, notion of nuclearity has very nice properties. But first, let me mention an exercise which is just very useful for understanding this whole, all of these notions which I mentioned. The exercise is that if A is smooth, for example, finite represented, and B is proper, then any functor from A to B is trace plus. So basically, it's functors from A to perfect K modulus. Tensor product with B. This is just equivalent to K-linear functors from A to B. It's a very good exercise on understanding how all these conditions interact with each other. Yeah. But notice that in particular it implies that a roller that any proper category is nuclear. Okay, now first I want to explain why this notion is shows up here. Why is it relevant for rigidity of motifs? And basically, how using this notion we will prove the rigidity in a straightforward way. First, so to prove rigidity of valid motifs over any base, basically, but in particular over K, we need the following. That, as Dustin explained yesterday, at least he formulated it yesterday, what we need is basically two statements, that the unit is compact, so the log of K is compact. So this is, of course, known. This is due to this already appears in the paper Bloomberg, Gebner, and Boada. Moreover, they show that basically maps from the unit object to a motif of some category is non-tense PC of this category. So yeah, this object is known to be compact, but more complicated statements which we need is that the category is generated by basic nuclear objects, generated by alignments of sequences x1, x2, etc. Such that each map xn to xn plus 1 is trace plus. Now, now let's observe that suppose that some category is nuclear. So nuclear objects of this category of categories, small categories, are curve over K, and also suppose that it's omega 1 complex. Then it follows by a simple argument that B is like a basic nuclear object in the category of categories. So then B is colimit of the sequence A1, A2, so on, such that each AN is finally represented, and each functor from AN to AN plus 1 is straight class. And we see that the log of B, universal best invariant of B, will be also the colimit of the same sequence. And all the transition maps will still will be a trace class. Basically, it's monodal functor takes trace class map to trace class maps. So it follows that so we only need to show that category of applied motifs is generated by colimits by object of this form. So the log of B, where B is nuclear. Only one moment. Okay, and now I want to say that this is actually pretty straightforward. Let's have to have the definitions. So basically, let's make the following observation. Lemma. If A is smooth, for example, finally represented, and B is any category of K, small stable input complete category of K, then functors, take functors to perfect K modules, take the tensor order with B, functors from A to B. This is fully faithful. And this is, again, it's kind of an exercise just to understand what smoothness means. Both categories are basically included, so both of these categories embed into A opposite tensor B. And this is just inclusion of subcategories inside A opposite tensor B. And now, if we know this, then we can deduce that the class.
Even like into the tensor B?
No, I'm talking about small categories. So the tensor product of small categories. I mean, okay, you can take incompletion of both of them, take the Lully tensor product, and take compact objects.
So you literally mean on the level of small categories?
On the level of small categories, yeah. If I'm working over a ring, for this proof, I don't actually need the level of categories. So it's just about small categories. Yeah. So corollary, the class of nuclear objects of cut curve is, so the first statement, which is already clear from definition, it is closed under finite colimits. And it's closed under semi-orthogonal equations. Under finite semi-orthogonal equations, but because it's closed under finite colimits, it's also closed under infinite semi-orthogonal equations. it's just corollary of it. But third, which is kind of less trivial, is that closed under taking full subcategories. Basically, if some category is nuclear, then its full subcategory is also nuclear. And this is basically a certain diagram chase. So if you have some B is nuclear and inside it you have some B prime, basically you take this functions from A to B prime. So functions from A to perfect K modulus tensor B prime. You have this comparison factor to functions from A to B prime, which is totally faithful. You want to know that it's equivalence, but you know that this is true for B. That for B you have an equivalence, but you also know that when you take the quotients of B by B prime, you have a fully faithful function. And together, it actually formally implies that here you will also have an equivalence. So it follows from very formal properties of this category of small categories.
Is it K-linear functions?
Yeah, functions K-linear and as a product of K-linear. So here we have fully faithfulness. And here it's basically a short sequence. These vertical arrows, they don't form a short sequence, but still already acknowledge the information which we already have implies that. So it implies that this B prime is nuclear. So we have these very nice properties of this nuclear categories. And now, so it remains to show that basically any category, at least let's say omega 1 complex category, can be resolved by nuclear categories. Let's do it just in essentially a canonical way. So suppose we have some C, which is perfect modulus over an algebra. So I just assume that the category is generated by one object. It's not really necessary, but I mean, actually, if we care about generating by limits, we can, any category is a critical limit of such, so we might as well assume this. And then we can define a K-enriched category, enriched in K modulus. Category B, let's say, such that objects of B are natural numbers, and morphisms from n to m. So this is R if n less or equal to m. If n is strictly less than n, then it is just the unit object, so it's K if n equals to n, and 0 if n is greater than n. The composition comes from multiplication in R. Then basically, then we have so if you just take functors from this enriched category, basically if you take Cauchy completion, there's notion of Cauchy completion in any enriched context. So if you just take functors from this B to K modulus and take compact objects, this is how Cauchy completion works.
Yeah.
Sorry?
Yeah.
The opposite is, thank you. And so there is just a quotient functor to perfect R modulus. So this is just a quotient functor. So you have a Schottky sequence. So this is a quotient functor and there is some kernel. And kernel is generated by okay, let's call this object, so this is not natural numbers, but let's call this objects like xn and xn. And kernel is generated by cones of the natural maps from hxn from the representable functor by xn to hxn plus 1. Basically, yeah, you do this funny construction with infinite semi-orthogonal equation into corpus of perfect K modules, but then you identify this exceptional object using these units in the mapping spaces. Yeah, and
oh, sorry, can you say again what's the surjection? Like the map?
You just this surjection basically each representable guy goes to R.
Okay.
Yeah. And so this is let's say that this is this construction, this whole funny way to represent perfect R modules as such equation. It is sort of familiar from syntactic geometry. Familiar to syntactic geometry. But I mean, there in that case, the idea is that in situations when there is a nice definition of morphisms for transversal objects, when Lagrangian submanifolds intersect transversally, like you have a nice definition of morphism in this case, but you don't have a nice definition of endomorphism of some object. And the way to proceed is basically take some generic sequence of Hamiltonian perturbations of this Lagrangian, and then you have the analog of this category where the maps are going in one direction, but then you can identify this acceptable object by using this canonical elements in Floyer homology. So basically, it's just a straightforward kind of generalization of that construction. But here we already have an honest one answer, but we still can do this final operation, and it turns out to be useful here. And so then by what I already explained there, so by the above.
You make the board a little bit?
Yeah, sure. So by the above, we know that this category in the middle is nuclear. So it has countable as a semi-orthogonal equation into corpus of perfect K modules. And the unit object is of course nuclear. And the kernel of that functor, the kernel is also nuclear because any full subcategory of a nuclear category is nuclear. And so we can, so basically, that's one way to prove rigidity of motifs over the base string. It's not the simplest way, but it's kind of it's a way to do this sort of in a most like uniform approach. So that it also applies. You can apply the same approach over a general rigid base. And now,
Sasha, could I ask?
Yeah.
I mean, but if you didn't know that the also category of nuclear was nuclear, couldn't you continue just making resolutions? I mean,
no, but I think it doesn't help because I think there is no reasonable conclusion about motifs when you only have a like this resolution by sequence. You're allowed only to use like short exhaustive sequences and critical limits, but what you are saying is it doesn't reduce.
it's like a geometric realization.
Yeah. Yes. Okay, so so it is actually crucial that taking full surface of the nuclear is again nuclear because everything else which I explained, it sort of generalizes almost immediately to the general rigid base. Well, the notion of nuclearity is not so straightforward to generalize because we use compact objects, and in that case we don't have such many of them. But still, it turns out that the whole proof can be generalized. So let me just explain the main ideas. What to do over a general rigid base. So consider general case. We see some C is a rigid category, and so we want good notion of nuclearity with basically with required properties, with the same properties. The most important one is that full subcase of nuclear history is nuclear. And so basically, let me formulate it as a fact. If you consider this category which is denoted by cut curve over C, so this is basically another way of looking at it is if we consider categories over C which are relatively completely generated. We can also consider dualizable, but it is sufficient when we deal with class motifs, it's sufficient to consider relatively completely generated. So it is completely assembled. And moreover, this Yaneda head functor from this category to its incompletion is symmetric monomial. It is automatically Oplat symmetric monomial, but it's actually symmetric monomial. This is not so difficult to show, but it's kind of very important for this whole story. And then we can make a definition that, let's say, B is nuclear if for any counter-represented object in cut C curve, which is only one compact. So if we write its y hat of this A as a colimit of the sequence A1, A2, and so on. Then we require that if we take the pro object, so we take the formal inverse limit of functors from A, functors, C-linear functors from AN to C, tensor tensor B. Sorry, it's a little bit confusing. Let's just say internal form. I'm taking internal form in the category of relatively completely generated C-linear categories. So I'm taking internal form to the unit object from AN and tensor this with B, and I require that as a pro object, this is the same as taking internal form from AN to B. This is basically the way to generalize this notion from the case when everything was completely generated. And then still this basic results about nuclear objects still holds, so you still have this generation by basic nuclear. And the only, so the main, so the most difficult,
Sorry, Sasha.
Yes.
Can you say how does this fit in this general framework of nuclear stuff, like basic nuclear stuff?
No, I mean the only reason why I had to make this tricky definition is because I don't have sufficiently many compact objects. So if I had sufficiently many compact objects, then like I could assume that A is this y hat of A will be just a colimit of the sequence of compact approximations, and then this will be just not only pro equivalent but already at each level this will be equivalent. So I'm simply generalizing this notion from the completely generated case to the case when our cases are not completely generated. This is just a natural way to do it. Or your question was different.
I mean, I was thinking you can also make this. Can you make this definition in the compactly separate case?
But I think I'm doing this.
Okay, that's what I was asking.
Yeah.
This is general notion.
Yeah, I mean, there are slightly different ways to do it, but they are equivalent.
No,
This is just one thing. Yes.
Is it so?
Is it obvious that Kepler C is yes?
It's not obvious, but you can. The same statement holds for Ivan algebras, which is quite formal, and then you can deduce deduce a statement for categories.
Also, could you remind us what relatively compactly generated means?
Well, okay, the base is rigid, so it's just a compact object. Relatively compact objects are just compact objects. I require that they relatively generate the category, which means that if you multiply them by object of the base, they generate the base. I mean, of course, this notion also makes sense when the base is not rigid, but let's just restrict it to the rigid case. So the most difficult...
Check again.
Sorry?
For this notion of nuclear to be well behaved, do you need one had to be symmetrical or will it work in the compact?
Well, I mean, at least you want the unit to be compact. I mean, yeah, this is slightly more than needed, let's just not search for minimalistic assumptions. Yeah, it's fine in this case. So the most difficult part is proving that if B is nuclear, then any subcategory is also nuclear. The analog of that statement. And here I mean subcategory like a subobject in this category. So it means that this B prime is generated by relatively compact objects. So this is the most difficult part. And let me just briefly comment how this works. In that case, like when the base was completely generated, basically just a case of K modules, we had this statement that this comparison functor was always fully faithful, and this was important in proving all these nice properties of nuclearity. But here, so we need to show basically that for any B in this cut curve, so if you consider and for any compact map in the case of Ivan algebras, so it's compact map in the case of Ivan algebras in C, we want the following kind of version of that. So we take representations of R in C omega. Let's work. Let's consider B. This is a small C enriched category. Instead of big categories, you can consider small categories enriched over C up to Morrill equivalence. So let B be small C enriched category. So we take this, we have a square, so representation of R in C omega, tensor B. So we go to representations of R in B. So we have now a similar category for S. And here we have a similar category. So representations of S in B. So again, B is a small category in C. So we have this commuted square, and basically what we want is to be able to construct let me be slightly more precise. So we have the square and denote by T. So this is F, this is G. The image of F. And denote by, let's say, Q, the image of G. So basically, we want to construct a functor from Q to this tensor product. So from the image, so this is roughly the image of the low horizontal arrow. We want to construct a functor from this to here, such that everything can use, all the triangles can use. And it looks scary, but this is possible, and you can actually do it in a sort of canonical way. Basically, like skipping the details. So this reduces to proving that there is a map of coalgebras, of E1 coalgebras, in the incompletion of the category of bimodules over S, which is S tensor S over R, Ionetta of this to Ionetta head of S. So basically, if you just like carefully, I mean like really carefully analyze what's going on here, then in the end you only need to construct this map of E1 coalgebras in the incompletion of the category of bimodules over S. So once again, from Ionetta of S tensor S over R to Ionetta hash of S. Both of these guys are naturally coalgebras, and you need a map such that after applying the Kalinin functor, we get the canonical map S tensor S to S in E1 coalgebras. In the case of E1 coalgebras, in the case of bimodules. So we have this canonical map of coalgebras, and you need to lift it to the map of coalgebras, E1 coalgebras in incompletion of bimodules. And this, so basically this map basically reduces to a version of the arguments, so due to Toyn and Baquet, using this in systems of bimodules arguments. So again, considering some in systems of formal canonics of square zero extensions. Yeah, okay, it's quite technical, but the idea is basically you want to generalize what you already have in the case when C was the category of K modules. You want to understand like how to obtain similar statements when you don't have sufficiently many complex objects in the base, and this is basically the way to do it. Okay. Yeah.
Can you explain again why this is what we need to show?
I mean, we wanted this for the faithfulness. I mean, in the ideal world, you can assume that this algebra R, for example, is finally represented, and then this is polyphasic function. But now the world is no longer ideal. It applies not only to the talk, but so you just want you want to at least have a map in a compatible way, have a map from the image of this functor to here.
Where is B prime in this story?
Sorry?
I just don't see where is B prime in this story.
What is the prime?
If I were to try to prove it like
It's the analog of the lemma.
It's the analog of the lemma. I mean, for the statement about subcategories, the crucial fact, I sketched this argument, so all we need to know is that these comparison functors are always fully faithful.
Okay.
Yeah, and this is the analog of that statement. Yes. Yeah. Okay. So this is like the sketch of how to modify all the arguments when the base is rigid but not completely generated. And now let me mention some applications. At least, well, let's say applications of the proof of rigidity and maybe of rigidity itself.
Sorry. in the previous case, if a category is just a module category of even algebra,
Yeah.
what does the nuclearity mean?
No, I mean it's still not trivial condition. It's a certain statement about all possible functors from the source to the target.
So there's no easy way to.
There's no no easy way, no kind of straightforward way to formulate it just in terms of the properties of the cell. Okay, so let's mention some applications. Let's work over the actual base. Let's consider, let R be connective P1 ring. Then when you take home, the mapping spectrum in localized motifs over the actual base, from the reduced motif of the flat affine line to the motif of R, you get the logical restriction, you get TR of R. And here it's like KCR, because of connectivity, this is the same as KCR definition, so this is inverse limit of reduced KCR over truncated polynomials in X inverse, if you do it canonically.
You're missing an omega.
Omega, yeah, okay. And the idea is that basically we can complexify the affine line by obviously projective line, and so after a shift, this reduced motif of the affine line, this is this is shift by 1 of the reduced motif of perfect object supported at infinity on P1 of this field vector. And this is a proper category, in particular it's nuclear. So this category supported at infinity P1. It has approximation by, basically naive idea is just to take degree Koch on infinitesimal neighborhood, but to be more precise, you need to take the decompletions. So it's like you take this is perimeter of perfect modules over the co-bar construction of this quantipotent coalgebra, which is S of X inverse mod X to the minus n dual. So when you take some co-augmented coalgebra with a quantipotent augmentation ideal or co-ideal, you can take co-bar construction, you get finally presented Ivan algebra. And yeah.
Before you continue, so that I'm not getting lost, what do you mean with the hat over you lock?
No, it's not a hat, it's supposed to be tilde. Just my right hand. It's reduced. It's modeled by, I modeled by the point, by the local. Yeah. So you approximate by this, and these are like essentially like Debekov of the infinitesimal neighborhoods, but also over integers. This will be literally the derivatives of finite genetic models over the z of x inverse, not x to the minus n. But here we need to be slightly careful because obviously s is not bounded above homologically. So we take this decompletion in an initial way. And this is basically it's approximation by finally presented object, but it's also trace class approximation because proper category is nuclear. So when you approximate by compact objects after passing to a subsequence, you can assume that all maps are trace class, and it follows that basically if you denote these approximations. If this approximation is denoted by an, then it follows that from this suspension of U log of the category at infinity, this is the same as inverse limit of K-theory of functors from the approximations. Home to u log of R. This is the inverse limit of K-theory of, it's omega. And K-theory is reduced, so functors from AN to u log of R. But then, by sort of Cauchy-Dualis, you get that this is the same as inverse limit of again omega of the inverse limit of reduced K-theory of R of X inverse mod X to the minus n. So which is what we needed.
So sorry, Sasha, can you explain the step where you go from the second to last horizontal line to the last horizontal line?
I should have mentioned the general lemma. So suppose we have some approximations. So suppose B is the element of a sequence n, and all maps are.
Why not Bn?
Why not Bn?
Yeah.
Let's make it Bn. And Bn to Bn plus 1 trace plus. So if you assume this, then maps in localized motifs from the motif of B to the motif of some category C. This is the inverse limit of K-theory of functors from Bn to C, which is in fact the same as inverse limit of K-theory of, so you can take the functors from Bn to in this case to SP omega to the unit object tensor C. And if you just apply it in this case.
Yes, but where did this come from again?
Just because, you can, there are, let's say, mysterious internal homes between approximations and C. These are difficult, but you know that up to pro equivalence, you can replace them by the name thing because of the trace plus maps.
Okay, so and then you're using at some point this.
I'm using the map from the unit object, this case here.
But are you using the statement about the inner arm?
No.
No, it's not required here at all. Yes.
It's a general statement, but it's not
More precisely, I have this auxiliary object which I'm mapping to internal home. So internal home is something very complicated. So I have this simpler modifications, then map it to internal homes, and when I say trace plus, already these modifications of internal home are sufficient. Yeah. So like the idea is that using the fact that transition maps are trace plus, I can basically replace the internal home with this.
So you don't need these facts about commutation of K-theory within.
No, it doesn't use this facts at all. Yeah. So today's talk is kind of more elementary. So it doesn't use this very difficult results. You get this, and in this particular situation, you get this identification with TR, and then kind of generalization of this. So let's say we consider some smooth scheme over some base. And I need to make this annoying assumption, which is very strong, that there exists smooth multiplication. Smooth multiplication. It is probably unnecessary, but it's not easy to remove it. Then, if you take KK theory, over the base, so it's triple K, over the base ring from perfect complex on X to perfect model. So if you take P homology, you get, if you just directly apply similar arguments, you get fiber of the map from K-theory of codification to continuous K-theory of the formal neighborhood of the infinity locus. But now this is the same as the fiber of the map from K of X to continuous K-theory of function neighborhood of infinity. Which, I mean, of course, the answer should depend only on X, not on the choice of computation. And actually, this fiber, of course, makes sense even without assuming that we have this smooth computation, but somehow I just needed. It's not so easy to get rid of this condition.
So, sorry, what is X hat infinity?
It's a function neighborhood of infinity. Puncture. You remove the infinity locus. Yeah. I mean, it doesn't depend on the choice of the computation. It's edge expression, and take this continuous basis. You have this by a similar argument, and so this is another kind of results of symbols of another computation of K homology or KK theory. Another statement of this sort is that suppose that the base is a regular Noetherian ring. K is the regular Noetherian, and X is proper over K. Then, if you take this K, basically K homology, so again, like K theory from perfect complexes on X to perfect K modules, you get a G theory. G theory of X, so this is K theory of coherent sheets on X. And at least in this special case, when X is just a closed subschema of K, you can just reduce directly deduce it from Bardak's theorem of the heart, using this approximation by finally presented elsewhere. But yeah, I mean, it requires some additional idea to prove this in general. And let me also mention the following: that we have this A1 invariant version of a classic motif. And let's just take the absolute base. So this is basically a module over the idempotent infinity algebra, which is geometric realization of classic motifs of algebraic synthesis. Algebraic synthesis are just basically in terms of algebras, you take just tensor product of copies of flat affine line, and this is naturally simplicial Ivan algebra. You take modules over this. This is idempotent infinity algebra, and you take the smashing ideal, which is the kernel of this localization. This is like what can be called subatomic classic motifs, and you have this functor like this can be denoted by I upper star, and this is like J lower 3. And then you can prove using similar ideas, basically similar methods of computing the mapping spectra. We can prove that for a connected one ring, R, we have, if we take mapping spectrum from J lower 3 of the unit, so basically of this idempotent infinity coalgebra, which is the fiber of the mapping, the unit to here. If you take this, take the mapping space to motif of R, you get the logical cyclic homology of R. Basically, you need to figure out what are the maps from the simplices if you take this reduced objects, like simply reduced in sequential sense. And then it turns out that if you just write down what happens, then you get the logical cyclic homology. Okay, and I have -2 minutes. Can I have two more? I just wanted to mention like how can you prove that the sketches of localized motifs are not completely generated, at least in some situations, or at least over some basis. So basically, the idea is the following. So suppose for simplicity, suppose that K is an intermediate row of Q. Just to simplify methods. So we consider this functor from motifs over K, so just HC minus over K. This is a functor to like U complete modulus over K of U. Over series in U, where degree of U, like cohomological degree is 2. So cohomological degree. And then this case is only locally rigid, so by the universal property you get of rigidification, you get refined invariant values in the rigidification of this case, which is nuclear. What I denote by nuclear theta, but let me just call it nuclear of K of U. It is also the same as dualizable inverse limit of modulus over K of U mod U to the n. So there's this, by the universal properties, there's universal way to refine our usual HC minus to this HC minus refinement. And then basically example, this, which is not so, well, it's not so easy, but you can compute this, that for K equal P of X, so if we take this HC minus refined of random polynomials, like over polynomials. So this should be idempotent with infinity algebra. This is basically, it turns out that this is over conversion functions on the intersection of a positive n of this subset where norm of u less or equal to the norm of the x to the n, which is non-zero. You take this intersections of the guys, take conversion functions on this, and this is a certain well-defined object of this nuclear category. And this is exactly the HC minus refinement of this. And this guy, it is not generated by compact objects. Objects of the nuclear category of Q of X of U. So it is not generated by compact objects. So these compact objects are just the usual perfect modulus of Q of X of U. And so you see that so corollary of this computation is that at least over this base, localized modulus over Q of X is not compactly generated. Okay, I'll stop here.